In this part of Chapter 12, we're going to talk about water and how water can act both as an acid or a base. Most of the acid-base chemistry that we're going to deal with will be taking place in aqueous solutions, meaning with water around. Now, water can act both as an acid or a Bronsted, so a Bronsted acid or a Bronsted base. And those species that can do that simultaneously act both as an acid or a base. I mean, not simultaneously at the same time within the same molecule, but the molecule itself can act either as an acid or a base. Those are called amphoteric molecules, and there's several of them. But water is one of those compounds. A small percentage, albeit is very small, but a small percentage of molecules of water can act as acids and bases, even in pure water without anything added to it. And how that happens is one of the molecules donates a proton to the other, to the next molecule. The one that's donating the proton acts as an acid, and obviously the one that's accepting the proton acts as a base. What is left over when this molecule gives off its proton? It's the conjugate base of this acid. And what is formed when my base grabs that proton is the conjugate acid of that base. This process is called the autoionization of water. Auto meaning self, so the self-ionization of water. Water is ionizing here, becoming two different ions. And there's always a little bit of hydronium ions. So this is a hydronium ion. 3 hydrogens bonded to the oxygen with a positive sign. So hydronium ion and a hydroxide ion. So these in pure water exist in an equal number, albeit very small, but they exist in equal numbers. We just said that there's always OH minus and H3O plus present in all aqueous solutions. In pure water, they're equal, but so if there's other sources of OH minus and H3O plus, then these are not obviously equal any longer. The product, so if I multiply the molar concentrations of OH minus and H3O plus together, it's a constant, and it's equal to 1 times 10 to the minus 14 at 25 degrees Celsius. Now, this product changes with temperature, but it's always constant at the same temperature. So at 25 degrees, which we will mostly use at this temperature, this is what the product is going to be equal to. That would be another one of those things that I would write down and tuck away someplace so that you have it handy to know, because it will be useful to you. Obviously, so here's mathematically what that looks like. The concentration and the square brackets in chemistry are going to denote molar concentrations. Remember the molarity, molar concentrations are going to be moles per liter. The molarity, or the molar concentration of the hydronium ion multiplied by the molar concentration of the hydroxide ion, OH minus, is always equal to 1 times 10 to the minus 14 at 25 degrees Celsius. So if the concentration of H3O plus increases, the OH minus concentration has to decrease for the product to still be constant and equal to this. Vice versa, if OH minus increases, H3O plus has to decrease. So if the concentration of one increases, the other must decrease to keep this number here constant. Let's do an example problem where we have to calculate, we have the molar concentration of one and we have to calculate the other. The concentration of the hydronium ions in the stomach acid is 0.1 molar, which actually we will learn it's pretty strong, okay, pretty acidic, which makes sense because it's going to break down our food. Calculate the concentration of the hydroxide ions in stomach acid at 25 degrees. What do we know at 25 degrees? We know that the product of the molar concentrations of these two ions is fixed and is equal to 1 times 10 to the minus 14. We can rearrange this equation since I'm solving for OH minus and I'm multiplying it by H3O plus. To isolate this, all I have to do is do the opposite of the operation that's already there. So if this is a multiplication, then I divide. So to isolate OH minus, I divide both sides by H3O plus. Whatever I do to the left side, I have to do to the right-hand side. So OH minus, so H3O plus times OH minus divided by H3O plus, H3O plus falls out on the left-hand side, is equal to 1 times 10 to the minus 14 divided by H3O plus. So this is how I rearrange this equation to look like this, to isolate OH minus. And now, to solve that, I know the constant and I know the molar concentration of my acid, so I can plug it in. 1 times 10 to the minus 14 divided by 0.1. That gives me 1 times 10 to the minus 13th molar, and that is the concentration of OH minus. Note that this is a very large amount compared to this. Very, very small amount of OH minus in stomach acid. Now you try your hand at this problem. Here you have the concentration of hydroxide ions, and you're asked to find the hydronium ions. So concentration of hydroxide ions in the antacid milk of magnesia is 5 times 10 to the minus 4 molar. Calculate the concentration of the hydronium ions at 25 degrees. We know that the product of these concentrations is equal to 1 times 10 to the minus 14, and we also know the OH minus concentration, so solve for H3O plus.